Okay. Remember back in chapter 2 when you were asked to figure out the number of subsets in a set? Well, in this chapter, to figure out the number of lines, or as I like to call them, rows, in a truth table, it's done the same way. You take, let me grab the black marker. You take 2 and then you raise it to the k power. Now in chapter 2, k was the number of elements in your set. Well, in this section, k is the number of variables. And like I said, we're only going to be using at most p, q, and r. So if you just had p and q, that would be 2 to the second, which is 4. And if we have p, q, and r, that'll be 2 to the third, which is 8. Now, I won't make you do truth tables that have more than 8 rows because it takes a little while to do those. So, but I might ask you the question, I'm sorry. If you had a P and a Q and an R and an S and a T, and I said, well, how many rows would that have? You'd be like, oh, well, that's 2 to the 1, 2, 3, 4, 5. 2 to the 5th, which is 32. Okay? So, anyway, that's how you calculate it. Okay, and now logically equivalent statements. Two statements are logically equivalent if they have the same variables. Get some colors here. With this color. Okay, they're logically equivalent if they have the same variables and I got the word and in here. And when their truth tables are computed, the final columns in the tables are identical. And those columns will have T's and F's in them. But it has to be both of these things. You have to first check, okay, this one has P's and Q's. Does this one have P's and Q's? Yes, okay. First barrier has been crossed. But then you have to go to the next one, do the truth tables for both of them, and then look at the final columns. If the one on the left is true, 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 false, and the one on the right is true, true, false, true. What did I just say? I said true, 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 false, and this one's true, true, false, true. They're not the same, so they wouldn't be logically equivalent. Even if they have P's and Q's in them, that last column has to also match. So it's got to be both. It's an and. It's got to be this and it's got to be that. Okay. All right. And De Morgan's laws are... We covered De Morgan's laws in chapter 2. They just looked a little different there. But for here, they look like this. For A, it says... if you have the negation of a conjunction, P and Q, it will be logically equivalent to if you were to do the negation of P and then the negation of Q, but instead of and doing an or, it's going to come out the same every single time. And so this dude, De Morgan, he messed around with this a lot, and he just kept finding it came up to be the same over and over and over and over, and he couldn't find any time when it wasn't true. And so he just, made it a law. He called it De Morgan's laws. Nice how he used his name, huh? And I always look at it as if it's kind of like distributing. It's like, well, maybe if I distributed the negation to the P into the negation to the Q, but then you have to change your and to an or, it works. And the same thing on the bottom one, kind of obliterated that, didn't I? The bottom one says if you have the negation of a P or a Q. That's a disjunction, which means you would do the disjunction first. You calculate P or Q. Do that first. Do this first. And then do the negation of that result. That works out the same way every time if you did the negation of P and then the negation of Q first, and then did a conjunction between the two of them. See how it's switching? So it's kind of like, in my brain, come on, pen. In my brain, I'm like, well, De Morgan says you could negate the P and then negate the Q, but then instead of an or, you'd have to switch it to an and. And it works every single time. And that's De Morgan's law. Which brings me to the My Math Lab part of the show where I start doing examples, so I will do these in another video.